Okay, so today we're going to be starting a new unit on probability and statistics. Today's section is 6.1, the counting principles. So we're going to be looking and finding the total number of outcomes for a situation. Probability is one of the most practical math applications to real life. We use it every day to determine how likely or probable something is to happen. We depend on knowing this for a lot of situations, like the probability of rain determines whether we're going to take an umbrella. The probability of winning a hand in a card game determines how much you'll bet. The probability of injury determines whether you'll participate in an activity, and the probability of making a team determines how much extra practice time you'll need. In order to calculate the probability that an event will occur, we need to learn how to count up the total number of outcomes possible. So we're going to do this by the fundamental counting principle, which allows us to determine the number of outcomes possible when dealing with a combination of criteria. So let's look at an example and use a tree diagram to find the total number of outcomes here. So let's say we're ordering a sandwich and we've got 3 different events or choices that we need to make. We can choose the type of bread, whether that's white wheat or sourdough bread, the type of meat, turkey, salami, roast beef, or ham, and we can choose the type of cheese, either cheddar or Swiss. So we're supposed to systematically match up each bread choice with each meat choice to determine how many different sandwiches we can make. So let's start up here with the sandwiches. So when making a sandwich, you got to choose what kind of bread you want. So we've got 3 options here. We've got white, got wheat, and we've got sourdough. Then after we choose our bread, we then choose our meat. Well, you can either make a turkey sandwich, a salami sandwich, a roast beef sandwich, or a ham sandwich. But we can do that for all of our different breads here. Turkey, salami, roast beef, and ham. And same thing here. Then, after we choose our meat, we now get to choose the type of cheese. So for each choice here, we can either put cheddar or Swiss on it. And that's going to go for all of these options. So as we get further and further down our tree here, we get more and more options. If you were to take the time to count up all of these options at the very bottom here, you'd see that you get 24 different possibilities here. So we can make 24 different sandwiches. So now we got to see if we can find a rule for determining the total number of outcomes based on the number of each choice. Well, we know that we've got 3 different types of bread. And we know that we've got 4 different types of meats. And we won't know that we've got 2 different types of cheese. And if we times those together, we actually end up with 24 different sandwiches. So looking at a more generic form of this, we've got that if we multiply the number of ways each choice can happen, we can determine the number of outcomes. So in event A, we have A ways, B, we have B ways, and C, we have C ways. So ours would be, for event 1, we'd have 3 different breads, so we'd put a 3 here. For event 2, we would have 4 different meats, we'd put a 4 here. And event 3, we'd have 2 different cheeses, we'd have a 2 here, and that would give us our 24 as the total number of outcomes. So let's look at a couple examples here. It says, in your closet, you have 9 varieties of shirts, 6 pairs of pants, 2 belts, and 3 pairs of shoes. So using this fundamental counting principle here, we can say we have 9 shirts, we have 6 pairs of pants, we have 2 belts, and we have 3 pairs of shoes, which is going to give us 324 different outfits that we can put together. Okay, now we're going to a deli, which we're going to buy lunch, and it includes a soup, a salad, and a beverage. So we can choose between chicken noodle soup, broccoli cheese soup, or potato soup. So that's going to give us 3 options of soup. And then we're going to choose either a garden or a Caesar salad. So we've got 2 options for salad. And then we can choose either Coke, root beer, Sprite, or Dr. Pepper. So we've got 4 options of drinks. And if we times all those together, we get 24 different types of lunches that we can order. So now an exam has 5 questions. 3 questions are multiple choice, and you can choose A, B, C, or D. And then 2 of the questions are either true or false. So we're just going to do this event by event. So for the first question, we have either A, B, C, or D. So we've got 4 choices. And then it says we have 3 of those. So for the first 3, we can do 4 for each of them. And then for the next 2 questions, it's either true or it's false. So we've got 2 options that we can choose from there. And that's going to give us a total number of 256 outcomes. Okay, so now how many different 4-digit pins are possible if digits can be used more than once? So if you look on your phone there and you swipe up and you're going to put in a password, there's actually 10 digits. There's 1 through 9 and then 0. So if we're picking our first number, we can do 10. If we're picking our second number, we have another 10 options, another 10, and another 10. So for a 4-digit pin where we can reuse the digits, we can do 10,000 different combinations. Okay, now Chris is designing a new board game and trying to figure out all the possible outcomes. How many different possible outcomes are there if he spins a spinner with 3 equal-sided sections labeled red, green, blue, and then rolls a 6-sided die? Well, if we look at the first event here, we're going to spin a spinner with 3 equal sections labeled red, green, or blue. Well, if you spin that spinner, you can either land on red, green, or blue. So we've got 3 options. And then if we roll a 6-sided die, we've got 6 options because the die has 6 sides, which is going to give us 18 different possible outcomes. So how many possible outcomes are there if you flip a coin 7 times? Well, I'm going to flip a coin once. I can either get heads or tails, so 2. I'm going to flip it again, heads or tails. And every time I flip that coin, it's either going to be heads or it's going to be tails. So I've got 7 different things here. We can either put that into the calculator or we can do 2 to the 7th. They'll both give us the same answer, which is 128 different outcomes. So how many different outcomes are there if you roll 2 fair 10-sided dice? Well, it's just another dice. This time instead of 6 sides, we have 10 sides. So we're going to roll the dice once, we get 10. We're going to roll the dice again, we get another 10. So we've got 100 different outcomes. Okay, so in all of the examples above, none of the choices were affected by one another, but sometimes they can be. So this is the difference between a dependent and an independent event. An independent event are when outcomes of one event does not affect the outcome of the other event. But a dependent event is when an outcome of one event affects the outcome of the other event. So all the examples above were independent. They did not affect each other. Let's look at an example of how they could differ. So if we have if we're making a 5-letter password and all letters can be repeated, there's 26 letters in the alphabet, so we can do 26 options for the first one, 26 for the second one, 26 for the third, 26 for the fourth, and 26 for the fifth, or we can put 26 to the fifth in our calculator, and that's going to give us 11,881,376. So a lot of different outcomes there. Now looking at a dependent, this would be, we're trying to make a 5-letter password if the letters cannot be repeated. So when I pick my first letter of my password, I still have all 26 letters. Then I go to pick my second, but I can't repeat a letter, so I've got 25. And then I've got 24 because I've already used 2 numbers. and then I've got 23, and finally I've got 22. So if I times all of those together, I get 7,893,600 possible outcomes. So it's a lot less because I don't have as many outcomes for each one of these where I did over here. I had 26 for all of those, and I have less and less as I keep going. So you must adjust the number of choices for the second event based on the choice of your first event. That's what makes this example a dependent versus an independent like the first one. So for each of the following, we're going to just choose whether it's dependent or independent. So for we roll a die, and then we roll it again. Well, the first time I roll it, I get a number, and then the second time I can still get that exact same number, or I can get another one. So this is going to be independent. Okay, now I'm going to flip 2 coins. I flip the first one, I either get heads or I get tails. I flip the second one, I get heads or tails again. So the one doesn't affect the other. So we're going to be independent again. Okay, now number 10. Pulling a card at random from a 52 deck of cards, setting it to the side, and then pulling out another card. Well, the first time I pull out of the deck, I have 52 options. And then the second time I pull out of the deck, I don't have 52 because I put one card off to the side. I have 51 options. So this one event depends on the other. So this is a dependent. Okay, now I choose a marble from a bag containing 20 marbles, and then I put it back in the bag, and then I choose another marble. Well, I have 20 marbles the first time. I take one out, I look at it, I put it back, and so when I go in again, I can pull out that exact same marble, or I can pull out a different one. So I have 20 marbles again. So this one's going to be independent. So we're electing a president, a vice president, and a secretary from a class of 25 students. Well, I have 25 students where I can choose any one of them to be my president. Then I'm choosing a vice president, but I can't have the same person be the president and the vice president. So I've already picked one of my students. Now I've got to pick one of the other 24, and then I've got to pick a third student that's not the first 2 out of my 23 to be the secretary. So this one is going to be dependent. Okay, now for a college application, Marcy must select one of the 5 topics on which to write a short essay. She must also select a different topic from the list for a longer essay. How many ways can she choose the topics for the 2 essays? So we've got a list of 5, and we have to pick one of them to write a short essay about. So I have 5 different choices I can make. Then I have to pick another topic, but not just another, a different topic to write a longer essay. So it can't be the first, so I only have 4 essays there. So I've got 20 different essays I can make here. And one of these, this 4, is dependent on which one you choose here. So that makes this a dependent. Okay, now we're going to look on the back side here. Okay, so for 14 through 16, the police use photographs of various facial features to help witness identify suspects. One basic ID kit contains 195 hairlines, 99 eyes and eyebrows, 89 noses, 105 mouths, and 74 chins and cheeks. One important thing to note here is it says 99 eyes and eyebrows, but that's 1 unit here. And then 74 chins and cheeks is also 1 unit. So we don't have 74 chins and 74 different cheeks. We can choose between 74 chins and cheeks, and they're like a package. So if we're looking at number 14, how many different faces can be created using this kit? Well, I've got 195 hairlines. I've got 99 eyes and eyebrows, which is a set. I've got 89 noses, and I've got 105 mouths, and then I've got another 74 chins and cheeks. And if we multiply all those together, we get a huge number here. That's all the different possible faces that we can use using this ID kit. So it's a lot of faces. But now a witness can clearly remember the hairline and the eyes and eyebrows of a suspect. How many different faces can be produced with just this information? We've got hairline, which we know is 195. And then we've also got eyes and eyebrows, which we know is 99. And if we multiply those together, we get 19,305. Okay, so now why would a tree diagram be a poor approach to determine the total number of possible faces this ID kit could produce? Well, if we look back at our first example, it was a pretty big tree diagram, and we only had 24 sandwiches, or 24 different outcomes. So now looking at this example, there's so many more outcomes that can come from this. So if we were to make a tree diagram for this, it'd be way too much. So we have way too many outcomes to make a tree diagram plausible. Okay, now looking at our last few examples here, at a certain point in history, the standard configuration for a New York license plate was 3 numerical digits followed by 3 letters. So we want to find the number of license plate possibilities if digits and letters can be repeated. Okay, so we know that a New York license plate is made up of 3 digits. So, and they can all be repeated, and we know that there's 10 digits for each of these. Okay, and then we've got 3 letters that can also be repeated. Well, we've got 26 letters in the English alphabet. So if we put that into our calculators, we get 17,576,000 outcomes. Okay, now we're going to do the same thing, but we're going to find the possibilities if letters and digits cannot be repeated. Well, we're going to pick our first one, which is going to be 10, because we have 10 digits. We're going to pick our second one. We can't pick the same digit that we picked for the first one, so we have 9 different options. And then we're going to pick the third. It can't be one that we already did before, so we've got 8 options. And then, for the same thing for the alphabet, we're going to have 26, the first one. We have 25, the second one. And we have 24, the third one. And if we multiply that all together, we get 11,232,000.